Welcome. In this video, we're going to solve some equations and inequalities that have just one variable in them. And this is going to be our, first lesson in Algebra 2. I'm going to start with these three examples that hopefully seem a little familiar from your Algebra 1 class, right? So the guiding principle here is that we need to be fair to both sides of the equation, right? Whatever we're going to do to one side of the equation, we got to be ready to do it to the other side too. So if I've got this x plus 5 equals 11, and we're going to try to do the same thing to both sides to access that x on its own on one side of the equation, we need to get rid of that plus 5. And so the opposite of adding 5 would be subtracting 5, so we're going to do that to both sides. So I'll start by subtracting 5 from both sides. Now you won't see me do this really past this lesson, okay, where I write minus 5. Minus 5, we'll just say I'm going to subtract from both sides, and I'll just say x equals 6, but we'll get there. Okay, for now, I'm going to say x plus 5 minus 5. Well, that's x plus 0, and that's just x. And this is going to be equal to 11 minus 5 is 6. Okay, that's how we solve an equation. Okay, this is the value. Pardon me. I thought I had my highlighter. This is the value of x that makes the equation true. There's only one value. Okay, as we move on through the course, even later in this video, you'll see there's times where every value of x works for an equation. Later on, there'll be 2 values, maybe 3 values. Maybe the next course you take, there might be an infinite number of values that make an equation true, but it isn't all of them. That's interesting. So we'll come over here and, okay, x is multiplied by 3 to get 21. Now, algebraically speaking, if you can just think of a number that you can multiply by 3 to get 21, well, you've solved that equation, right? That's the nature of algebra. But if you can't, what we're going to do is we're going to undo the multiplication by 3. So we're going to divide both sides by 3. Now, I might call this multiplication by 1/3. Okay. Which on the right, I'll just interpret as division by 3, because I know what 21 divided by 3 is. Okay. So 1/3 of 3x, well, that's just going to be x. And this will be 1/3 of 21, is just 7. Okay. And that's the solution to my equation. Okay. Now on this third one, we've got 2/3. So we need to get rid of that. We need to get 1x. So I think about what's a number that I can multiply 2/3 by to get 1, and that would be 3/2. So I'm going to multiply both sides of this equation by 3/2. Let's see, is that still visible to you? Just barely, so maybe we can solve that over. Okay, now, I'm just going to have 1x, so I'll have 6 divided by 6x, so that'll just be 1x, equals 12 times 3/2. For me, okay, if I think about it really hard, I could see it. But I might instead just say 12 times 3, I know that's 36. 36 divided by 2, that's 18. Okay, so x is going to equal 18. And that's the value of x that makes the equation true. Now let's add in a second step. Let's solve some two-step equations. All right, now these equations are going to be pretty much the same. We're just going to have to do a first step before we're ready to solve at it, right? So 2x minus 1 equals 3. We're going to want to get rid of that minus 1 first. And now I will say that in general, we're kind of algebraically solving is a backwards type operation. So, we kind of want to go in the reverse order of PEMDAS. So if, in computing a number, we deal with the grouping symbols or the parentheses, and then the exponents, and then the multiplication, division, and the addition and subtraction last. When we're solving backwards to try to find x, we're going to start with the addition and subtraction, then do the multiplication and division, and then eventually, not right now, it'll be a while before we have to deal with exponents, but then we'll deal with the exponents, parentheses, all that stuff. So what I'm saying is if we're going backwards, we want to start with addition and subtraction. Now I'll show you that that's not a must. I'll show you why it's not a must, right? As long as we're just being fair to both sides, we can always solve our equation. But it will go better for you if you deal with this minus 1 first. So I'm going to start by adding 1 to both sides. It's going to be 2x equals 4, and then I'm going to divide both sides by 2. And I got x equals 2. That's great. Okay. Hopefully this seems a little familiar from a previous class. I will also show you that a person, and if you're dissatisfied with that, good for you. Just be happy with that. But a person could divide both sides of this equation by 2, right? It wouldn't necessarily be wrong. I don't want you to think, oh, if my first step was divide by 2, I'm toast. I'm not going to get the right answer. Because that's not true. Okay.
we're going to divide everything by 2. And this is where I feel like you might actually just make an error if you were trying to divide both sides by 2. Right? Because we're going to have to divide everything by 2. We got to be fair to both sides. So half of 2x, that's 1x. And half of -1 is -1/2. And then 3/2. Then I could add 1/2 to both sides to get 4/2 and say, oh yeah, x is 2 again. So it's not like you have to do it addition and then, undoing your multiplication division. I just think it's the best way for you to go, especially at this point in the year. All right, now I'm going to do one more. I'm going to add 5 to both sides. So I'm going to add 5 here and there. And then I'm going to have 1/2 x equaling 15. Okay? And then to get rid of that 1/2, I'm going to multiply by 2. And then 2 half x's is going to be an entire x. And so the x is going to equal 30 here. Okay? Now for 3x plus 1/3 is equal to 1/2, okay, I'm going to take the same approach. I'm going to deal with the addition and subtraction first and then deal with the multiplication and division. But this 1/2 minus 1/3, that's going to need a little more work. So I'm going to go over here and I'm going to say, all right, I'm interested in doing 1/2 minus 1/3. And me personally, I've found this arithmetic to be something I just kind of remember and it's been kind of useful to me. I don't know if it would be useful to you, but I'll show you how you get it. Okay, we're going to get a common denominator of 6, right? Because 2 times 3 is 6. And so 1/2 is 3 over 6, and 1/3 is 2 over 6. So their difference would be 1 over 6, right? So if I was to say, all right, I'm going to subtract 1/3 from both sides, then I would have 3x equals 1/6. And I feel like right here is where we could really start to make an error. Taking a fraction and dividing it by a number, that's why I would recommend when you're kind of dividing both sides of an equation by 3, and I did it over here. Back a little earlier, I did this one with division. Anytime you're dealing with fractions, I would recommend multiplying by the reciprocal, because it's a lot easier to multiply a 6 by 1/3 than to divide it by 3. Yeah, I could really easily see you making the error where, oh, a 6 divided by 3, that's going to be a half. That's not what it is, right? We just multiply straight across and we say x equals 1 divided by 18. Okay? And that's the solution to that equation. And the big takeaway so far is that, at least with these linear equations in one variable that we're dealing with right now, we can solve these equations by adding the same number to both sides of the equation or multiplying both sides of the equation by the same number, right? All right, now let's talk about a situation you may have forgotten about since Algebra 1 or whenever you last took an algebra course. And that's the no solution or infinitely many solutions situation that typically comes up at the beginning of an algebra course and then not very much after. I just need to remind you, and mostly what I'm trying to remind you of right here is the distributive property, at least in the example on the left. So we're going to go over here and we're going to multiply the 2 by the x and the plus 3, because if we're multiplying x plus 3 by 2, we need to double x and we need to double 3 also. Okay. So I've got 2x plus 6 minus 5 equals 3x, and then this is another multiplication. I'm multiplying that x minus 1 by a -1. Or you could think about, okay, I'm going to subtract an x and I'm going to subtract a -1, and subtracting -1, that's like adding 1. Either way, that's going to be 3x minus x plus 1. And then I'm going to start to combine like terms, something I realize I'm kind of just assuming you already know how to do, but I don't think it's too much for me to expect you to know that x's can only be added to x's. That, for instance, 2x plus 6, that's not going to be 8x. Okay, that's just 2x plus 6 because it's like adding dollars and cents, right? So that's a different discussion. So we're going to combine like terms. Okay, so plus 6 minus 5, that's going to be 1. And over here, 3x minus 1x, that's 2x. plus 1. And so I'm seeing the same thing on both sides of the equation. If you just see that and you remember, well, then that's how I know I have infinitely many solutions, or all real numbers work for this equation, or any x you can think of makes this equation true. It's always true. There's a number of ways we can say it. I'm just going to say all real numbers. Because, pardon me, I didn't whittle this all the way down. If I subtracted 1 from both sides of the equation, I have 2x equals 2x. Or if I subtracted 2x plus 1 from both sides of the equation, I've had 0 equals 0. And so that's how I know that I've got all real numbers, infinitely many solutions situation. So there's not a number that you could think of to plug into this original equation right there and have it come back not true. It's always going to come back true. Okay, then on this next one, 4x plus 5 equals 4x minus 10. Unlikely, right? You take a number and you add 5, take that same number and subtract 10. It's going to be two different things, right? They can't be equal. We know this. But let's get it to something a little more clearly contradictory. Let's say subtract 4x from both sides. Okay, and then I'll be saying 5 equals negative 10. And that's just not true, okay? So it's saying that this equation is true, this original equation right here is true as often as 5 is equal to negative 10, which is to say never. So I'm going to say no solution. And to summarize, I would say that you're going to get no solution anytime you are looking at something that's like 0 equals 1. Two numbers that are not the same on opposite sides of the equal sign, right? That's just anytime that what you're seeing is blatantly false. So let's say, okay, this is clearly false. And infinitely many solutions, that I feel like that can take a few more forms, right? That we could see 0 equals 0. We could see something like x equals x. Something that's always true. Okay, and that's how we know we're dealing with one of these situations. But let's move on and solve some inequalities now. All right, so my advice with inequalities is that you want to solve them the same way that you would solve an equation. Okay? The only thing you need to worry about, and I'm going to actually write this in on the right side, and that's that the direction of the inequality is going to reverse when we multiply both sides of that inequality by a negative number. It has to be multiplication and it has to be negative, right? Or division, but no adding a negative number isn't gonna flip it. And I'll go back in and talk more about why that's true at a different time. For now, we just need to remember that it shouldn't happen too much at the beginning, right? Because we're not dealing with the most complex inequalities ever. So we're over here, half of x minus 5 is less than 10. Remember that right here, the one that looks like an L is less than, or you can remember that the alligator eats a bigger number, so on the 1/2 x minus 5 side, that's the less side. Okay, so I'm going to do the exact same thing I did when I was solving this equation when it had an equal sign in there. So I'm going to start by adding 5 to both sides. And then I'll have 1/2 x is less than 15. And then I'm going to multiply both sides by 2. And it was x is less than 30. Okay. Now, you see, I'm going to ask for your solution as an inequality, as a sketch, and as an interval. Hey, you probably, I won't say probably, you might not know about interval notation yet. That's okay, I'm about to show you. Okay, inequality, that's what we just did. Okay, we've got x is less than 30. The sketch is like, okay, if we were going to draw a picture of this set of numbers on a number line. Okay, well, we just want everything to the left of 30. Everything where x is less than 30. So there's 30. Get a better circle than that. Yeah, that's going to be 30 on my number line. Okay, we want everything to the left of 30, but since it's strictly less than 30, we don't actually want 30, because 30 is not less than 30. And so we leave the circle open. And when it says interval, we'll come back at that at the end of the video.
Okay, so we're gonna skip that for now, and we're gonna come back in a minute. All right, so here we have 2x minus 1 is greater than or equal to, that's that extra line on the bottom, means it like allows for the possibility of equality. So we're going to go over here and we're going to add 1 to both sides, just like if it was an equation. I feel like this is one that we also solved when it was an equation, so it should be pretty familiar. Yeah, 2x is greater than or equal to 4. I'm going to divide both sides by 2, and my inequality will be x is greater than or equal to 2. Okay. To draw a sketch of that, okay, well, I'm going to put in 2 on my number line. Go over here. Okay. And we're interested in shading where x is greater than 2. Give it a little more arrow to emphasize it. And also where x is equal to 2. Circle's filled in because it's greater than or equal to, right? If we see that greater than or equal to, we know it's going to be a filled in circle. And again, more on that as we're moving forward. All right, so let me tell you about the interval notation. These first 2 intervals you see they're like finite. What we would call that is that it's a bounded interval, right? It's not infinite. Okay? And, you know, the fact that both circles are closed in the top one, that does mean it's going to be a closed interval, and the fact that -2 to 2, that those are both open, that would make it an open interval. But those type of open and closed sets, that's not really what we're here to talk about today. We're here to talk about some inequalities, solve them, and get some solutions, right? So we're going to say that inequality for 4 to 14, it would be 4 is less than or equal to x, and x is also less than or equal to 14. Okay? And I'm going to keep kind of doing the same here. And let's see, x is bigger than or equal to 10 down here, and x is strictly less than 0 or negative down there. Okay, still on my shot. Okay, and then I'm just going to show you how to write these as an interval because I just don't think it's that big of a deal. Okay, 4 to 14, we're going to say 4, comma 14. And since we're including both of the endpoints, we're going to use square brackets. Okay? Anytime we're including the endpoint, we're using square bracket. Okay? -2 to 2, okay, same idea, but we're not including the endpoints, so we're going to use a parenthesis. I feel like the parenthesis is a bit of a, not the best notation ever, right? Because that looks like the point in the xy plane where x is -2 and y is 2. So we'll just have to know that context will dictate whether we're talking about an interval or a point on the plane. Okay, x is greater than or equal to 10. It's like, well, there's no upper bound. This is an unbounded interval. It goes all the way towards infinity. So what we're going to write is 10 up to infinity. Now we're going to include 10, but we're not going to include infinity. We're never going to include infinity because infinity is not a real number. X can never equal infinity. Equals is a relationship between 2 real numbers. Okay, so if x can approach infinity, it can get really large, but x can never really equal infinity if x is a real number, because infinity is not a real number. I think that's enough on that. Then over here, when x goes below 0, it goes from 0 at its greatest all the way towards negative infinity. So we're going to say negative infinity up to 0. Okay? The circle on 0 is open, so we're not going to include 0. And we never include infinity, so it's going to look like that. That's interval notation. So now we can go back in here and write the solutions as intervals, right? X is less than 30. Okay, well, that'll just be negative infinity up to 30, not including 30, because it was strictly less than, and not including negative infinity, because we never include infinity. Okay? And then the second one, I can say x greater than or equal to 2. Okay, well, I'm going to start at 2, and then I'm going to go up to infinity. I'm going to include 2, indicating that with a square bracket, and then infinity, always a parenthesis. Right? Don't even think about it. Just always parenthesis if there's infinity. All right, now I'm going to wrap this video up with a few more practice problems for you. Going from an inequality or a statement to an interval, or from going from an interval to an inequality. So I'm going to tell you, you need to pause the video right now because the answers to these questions are going to pop up in just a few seconds. All right, there you go. I think I'm going to tell you, if you need any support on any of these items or any of the other things we did in this video, you should come see me. Otherwise, thanks for watching.